Okay, so hello class, welcome to yet another week of Introduction to Photonics course. And now in this course, we'll be moving on to a bit advanced topic. From all the linear phenomena, we'll be moving on to some linearity. Okay. So let us now begin with the nonlinear optics. Okay. So my first question to you is, what do you understand by nonlinearity? Someone joined. Huh. What happened? Just a second. My first question to you is, what do you understand by nonlinearity? I need some answers, please.
To get some non-linear response at the output.
What do you mean by nonlinear here? What do you mean by nonlinear here? What do you mean by nonlinear here? Why can't I select an eraser? What do you mean by nonlinear here? Yeah, what do you mean by nonlinear?
It deviates from its path. It does not remain constant.
Yeah, sort of like that. It is deviating from its own path. That means if I say x is proportional to y, so it's a linear relation between x and y. Now, I say that x is proportional to y, yeah. Or I say y is proportional to x squared. So this is a quadratic relation, right? It will be something like parabolic, right?
Yes.
So this is non-linearity, something that is not linear. That's what it means, non-linearity. So all this while we have been seeing linear relationships between our quantities, whatever we were considering, like the displacement vector has a linear relationship with the electric field, the polarizability has a linear relationship with an electric field. So when we talk about non-linearity, then we no longer look at the polarizability polarizability's linear relationship with electric field. That is, we say we were first considering that this polarizability is directly proportional to the electric field, and there is some constants like the electrical proportionality constant, like the epsilon and the electrical susceptibility. That is, P is equal to epsilon chi E. But this is just a part of the whole general equation of polarizability. So this is a linear relationship, but that's not the true picture or all picture. That's not the full picture. Picture is yet to be completed. So with that, we come to our very first question of the session. What is the general equation of polarization? So I said that P proportional to E is not the general equation. It's just a part of it. So what is the general equation? A. Deepatin says A. Anyone has any other answers?
Option A.
Yeah, option A. Option A is the correct answer. So, okay, option A is the, sorry. Here I wanted to discuss something. So this is the correct answer. That is the, if we want to expand the polarizability, that polarizability will be equivalent to epsilon 0 times chi e plus chi 2 e square plus chi 3 e square. Okay, and all these different terms have certain physical significance. Okay, so this is just that we were doing is known as the first order relation of the chi, or this chi over here is known as the first order chi, or first order electrical susceptibility. Okay, now this is a second order chi. Okay, this is second order chi. And similarly, as you go on progressing, we'll have third order, we'll have fourth order. Okay, third order or fourth order, like that we'll get chi. So it depends on the material. Actually, the thing is, like, we were dealing with the material that has a very high first order chi and very low second order and third order chi, and therefore those terms are close to negligible. That's why we don't take it into account in our general in our relationship, in our linear and therefore we get the linear version of P is linear to electric field. Okay, so whatever graph we draw with polarization with E, it's something like this. So if I intend to draw P versus E, so this is my polarization and this is E, what we usually used to get, we used to do a linear relationship. Okay, it used to be something like this. Okay, but at certain point of time, the non-linearity sets in. Okay, it would be something like this. It would go something like this. This is what you call as the nonlinear response. Okay, this is what you call as a nonlinear response. So now I welcome all of you to the domain of nonlinear optics. Okay, so nonlinear optics is all about studying these different higher orders terms which are there in this polarizability equation. Okay, so let us move on. Okay, so okay, you guys saw the answer. The refractive index. So now we have seen the relationship of polarizability with that of the electric field. So do you think that the refractive index of the material also changes with light intensity? What is light intensity proportional to?
Energy.
In terms of the electric field, intensity is always dash of the amplitude. Intensity is proportional to what? Something of amplitude, directly proportional to the amplitude.
Power.
Square of the amplitude. I hope you guys know this, right? This is general class 12th standard stuff. Intensity is proportional to the square of the amplitude. So here also we have a refractive index of the medium changes with the light intensity. Is this true or false? Is it true or false? Can I get some answers, please? Okay, I'll tell you the answer. The answer is true. Why do I say that? Can anyone guess? Yeah, the Patel has said true. And why do you think we say that it's true? Why is it true? You must be having some arguments, right? What is the argument for that? Okay, we say that the displacement vector is equal to epsilon 0 r e. right? This is equivalent to epsilon 0 1 plus chi e. And here 1 plus chi, what is epsilon 0 1 plus chi e? That is equal to the polarizability. And we open the polarizability in this term. Epsilon 0 chi e plus chi 2 e square plus chi 3 e cube plus blah 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 blah. So epsilon r is equal to what? 1 plus chi. So now we keep on opening the sky. My eta n is also proportional to chi to the power half, and if we try to solve this, we'll have this e square term in the account, and my actually refractive index of a medium would be like n plus a1e plus n plus a2e plus n through like this. It will go on, keep on going. And now here these are some coefficients, and we write the general equation as n is equal to n minus half of r n cube e minus half of something something. It will go on and go on. Now here r, what is your r? R is your electro-optic coefficient. Okay? So R is your electric optic coefficient. So. Then this can be a linear effect and a nonlinear as well. So when your n is, if I plot n of e with e, you'll find these things in the textbook, Fundamentals of Photonics, Saleh and Tech. So if you try to plot this, it would be a linear relationship. And this is true for a Pockel's medium. Okay, Pockel's medium has linear electro-optic effect. Okay, the linear electro-optic effect. Here the birefringence, the polarization, these are all the proportional to the first power of E and the applied voltage, just the first power of E. Okay, proportional to the first power of E. While if you see some non-linear relationship between the refractive index of a medium and the electric field, then we enter a domain of nonlinear effects. Okay, so now let us move on to the next question. So do you guys know what is Pockel's effect? This is a very basic question. What is Pockel's effect? I expect
It's
some
a phase
answers.
modulator.
It's a phase? Yeah, you're on the right path.
Phase modulator.
Yeah, Pockel's effect usually is modulation of the phase of the light which is interacting when it is passed through certain medium. That is, the phase of an optical wave through a medium can be modified, okay, with an applied electric field. So with that, we will talk about that how Pockel cells work. So this question that we have over here is based on a Pockel's effect. Okay, so we have a gallium arsenide crystal. The refractive index is given, and the electro-optic coefficient. Electro-optic coefficient is that R that I showed you. That is known as the electro-optic coefficient. The electro-optic coefficient is also mentioned, and at what wavelength my light is going, that is also given, 1.3 micrometers. And we are also being given information about the length of your modulator. And this is in this electro-optic modulator, we have kept this gallium arsenide crystal. And the electric field applied to the modulator is 10 to the power minus 3 volts per meter. Okay, so can you draw a picture of it, how the cell will look like? So this is your whole modulator. Okay, see, So this is a cell. This is what I'm drawing is a Pockel cells, and these are the electrodes which I've put over here. And through these electrodes, what I'll do, apply some field to this cell. Okay, this cell, some field, and this field is 1.62. Field is 10 to the power minus 3 volts per meter, and here goes my light. So what we are doing, we want to modulate the phase of this light which will come out of this cell, and that we are doing using this whole effect, a whole electric effect, which is a linear phenomena. So your question is the half wave voltage for the above modulator. So before moving on, tell me, what is the half wave voltage? What do you understand by a half wave voltage?
V pi.
Sorry?
V
V
pi.
pi. What is V pi? You said V pi. V pi is the notation which is used for denoting a half wave voltage. But what does that V pi do? What is that voltage? What it does? What it does? What does this V pi do? Did you understand? Sir has mentioned clearly. So, let's say this would be the phase of my what? Of the light. Okay, phase of this thing, and this is the initial phase. So there will be a change of phase. So the change of phase will be given by this. R is the electro-optic coefficient, N cube E times L. L here is the length of the modulator. So here what is your delta phi? Delta phi means the change in phase, the phase difference. So here, which one is your delta phi? Which term is your delta phi over here?
Negative.
The negative term, right? That is 2 pi by lambda times 1 by 2 r n0 q e times L. Okay? So here what happens, we are asking about the half wave voltage. We say that there is a modulation of the phase, that is phase of the radiation has been modulated, and what we are doing, we are applying some voltage to my whole modulator. Okay, inside which you have some material. Okay, material of certain refractive index and have some coefficient, a high coefficient of the electro-optic coefficient, of whose value is high. So how much voltage should we apply such that there is a phase change by pi? Now I would ask you, when we have a phase change of pi, what is the significance of this phase change pi? What happens? Remember in interference what we studied?
Destructive interference.
Yeah. So pi, delta phi is equal to pi. So half wave voltage. Half wave voltage is V pi, where your delta phi becomes pi. The minimum amount of voltage that is applied to your electrodes where the delta phi, the change in the phase, the difference in the phases would be pi, and this is pi. So this will be 2 pi times lambda by lambda 1 by 2 r n0 q. Now we are giving some electric field. We can write the electric field in terms of the voltages. Okay. So I hope I can get an answer for this. What is electric field in terms of voltage? I want
V
others
by
also to... Tell me, Deepatil.
V upon D.
Yeah. So I want others also to participate in this. Okay. V by D times L. Okay. And what is D over here? L is something, D is something. So I have this cell. This is my Pockel cell. The length of the cell is L. But I am putting some voltages across the electrodes. Okay, so this is my electrode. Here I am giving some V pi, and this is my ground. So the separation between the two electrodes, okay, there will be some separation between the two electrodes. This separation between the electrodes is D. Okay, so this is my V pi. So I'll term this as V pi. So what is my V pi? V pi is equivalent to lambda by R n0 cube times D by, is it right? Yeah, D by L. Okay, so this is V pi. So this is the formula which you have to use to find the half-wave voltages. We have all the relevant information given to us. Okay? Alright, I would urge you to please check the values and let me know if there is any discrepancy. And this will be in volts. Okay? Okay, you guys got it? Okay. Now moving on to the next question. See, I had applied some voltage that is giving me a phase difference of pi. We call it a half-wave voltage. That is V pi. Now suppose I have this cell of mine and I'm changing my voltages. Okay, I'm varying my voltages. Okay, this is V. I'm varying my voltage from 0 to 4.45 volts. Then what will be the phase difference achieved? How do you solve this problem?
Using the same formula.
Exactly. We'll use the same formula, but we'll use certain mathematical trick. We'll have to do some math. Okay. So phi is equal to phi 0 minus r pi n cube by lambda 0 times V by D times L. Okay. So this is again equivalent to, I'm just writing it as pi V by V pi. Why? Because my V pi is equivalent to, what is my V pi equivalent to? The one which we used before, right? That is equivalent to lambda by R n cube, sorry, lambda 0 by R n cube times D by L. Okay, so here it's exactly reciprocal of that. L by D Rn cube by lambda 0. It's exactly reciprocal of it. So that will be equivalent to phi 0 minus pi V by V pi. So now what are we going to do? So this is my phi. Phi is equal to phi 0 minus pi V by V pi. Okay. Now let's see what are we going to do after we got this. So I have my V1 as 0 volts and V2 as 4.5 volts. So let's say phi 1 is equal to phi 0 minus pi V1 by V pi. I hope everyone understood how we got this formula. All good till now? Okay, I'll assume that all good, all of you understood. So now V1 is equal to 0. What is my V1? V1 is equal to 0. So my phi 1 will remain as phi 0. Okay, we aren't applying any electric field. So there will be no modulation of the phase. That will remain as it is. Now phi 2 is equal to phi 2 minus pi V2 by V pi. That is equivalent to this. Okay, my V2 is 4.5 and we have already calculated V pi before. Okay, so we'll use the V pi which we have calculated in the previous question over here. Okay, and we'll calculate it and we'll get this. So what will be my delta phi? That will be phi 1 minus phi 2. Just do phi 1 minus phi 2. Phi 1 is phi 0. So phi 1 minus phi 2 would be phi 0 minus of phi 0 plus 0.847. Mind you, this is in radians. Okay. Now let's move on to the next question. So in this Pockel cells, what we can do, we can modulate the cell. Now if we put this Pockel cells into a Mach-Zehnder interferometer, then you know what we can do? Do you know what can we do? We can do an intensity modulation also. All clear? So our next question is based on this. So if the intensity coming in is I0, then the intensity coming out would be I0 by 2 into or times 1 plus cos of delta phi. Okay, that will be the intensity which we'll get out of this. So if the above modulator is used as an arm of a Mach-Zehnder interferometer, then what would be the output intensity in terms of I0? I0 is the output intensity when my V bias is equivalent to 0 volt. Okay? So how are we going to do this? We will use this formula. V out is equal to I0 by 2 times 1 plus cos of delta phi. That is equivalent to I0 by 2, 1 plus cos of 0.847. This will be in radians, okay? Just calculate what is going to be. I hope all good. You understood this point, right? You understood the whole flow of the question, right? This question was given to make your concepts clear about how our Pockel cells work, how the phase gets modulated. So what do we learn from this question? Working of a Pockel cell, how it works. Okay, so basically there is phase modulation by varying the voltage. Phase modulation how? Phase modulation is done by varying the voltage. Varying the voltage which is applied to the electrodes that is connected to your cell. Now put this cell in a cell ko or put it in a Mach-Zehnder interferometer. Okay, and what will you able to do? You will be able to do an intensity modulation. Okay, I hope you understood Pockel's effect with this question. Did you understand Pockel's effect with this question?
Yes.
Yeah, good. Very good. Okay, so which of the following does not depend on Pockel's effect? Intensity modulation, phase modulation, or optical switch? It does not depend on Pockel's effect.
Option C.
Sorry, the question says which of the following does depend on Pockel's effect?
A and B.
A and B. And you don't think optical switch depends on Pockel's effect? Well, the answer is C as well. Optical switch also depends on Pockel's effect, where you can use the voltage to modulate the intensity. Optical switch is because switching the light on off, switching from one to other. Okay, that's how an optical switch is used. So I would urge you to get more information on optical switch. I don't know if that's in the course of your syllabus or not, but it's good that you read about optical switch also. Okay. A very interesting thing. A summary of all what we had done in the past, 2 weeks. I want you guys to answer this. Just look at the chi values, what order chi is used, look at the electric field and magnetic field used, and tell me what would be the answer. So let's start with the Pockels and the Kerr effect. Faraday effect you must have studied long time back. But Faraday effect, it's easier to do. What is Faraday effect? What does Faraday effect do? Faraday effect, C. Yeah. Oh, acha, you answered it correctly. Yeah, I have given the answer. This thing is, C is the answer. So Faraday effect. What is Faraday effect? Causes polarization, rotation by certain angle. Now this polarization rotation is proportional to the what? Projection of magnetic field. Projection of magnetic. Oh no. What have I done? Keep. Sorry. I wanted to do something. I did something. I'm sorry for this. Okay. So Faraday effect causes polarization rotation to the projection of the, which is proportional to the projection of the magnetic field along the direction of propagation. Propagation of what? Along the direction of light propagation. Okay, that is Faraday effect. So a magnetic field is required. So my C goes to 2. Okay, this is how you try to answer match the following questions. Okay, then is your, I would ask Deep Patel to do the next. Say Pockel's effect. Deep Patel, you answered it correctly. So where will Pockel's effect go to? Deep, can you hear me out?
Yes.
Pockel's effect go to?
One.
B goes to 1. Why do you say it's 1?
Because it is second order.
Second order kind. Now, and electric field is at time F and at time 0. Okay. Now, Kerr's effect. Who will go for Kerr's effect? Kerr's effect is a nonlinear phenomena proportional to E square. So that will go to 3. And so we are left with the last option, which is for the second harmonics, that is A. So this is how you solve the match the following. Okay, so Kerr's effect is actually, we already did for Pockel's effect, which was the phase modulation. Now we will introduce Kerr effect. Kerr's effect is the nonlinear interaction of light in a medium with an instantaneous response and this is related to the nonlinear electronic polarization. Now here when I say polarization, don't think that this polarization is that bifringence polarization. This polarization is the electronic polarization. That polarization, changing the direction of the that electric field we studied, changing how the electric field vector is moving, or the tip of the vector of the electric vector is moving. That is your optical polarization, and this is your electronic polarization. Okay, it's related with the medium. Okay, and that the polarization, optical polarization, which we talk about, that is related to the light wave which is propagating in a medium. And this polarization is a medium property, and the polarization, optical polarization, is a property of the EM wave itself. Now we'll do a question which is based on Kerr's effect. So we have a 5 milliwatt laser beam. Now it is propagating in a single mode silica fiber. In this silica fiber, we have a Kerr index of 3.2 10 to the power minus 20, and the effective cross-section area is 50 micrometer, and the distance that it can travel such that the phase accumulated due to self-phase sorry. Can you see the screen?
No.
No. Just a second. I'm sorry for this technical glitch. Can you guys see the screen now?
Yes.
Yeah, I'm so sorry for this technical glitch. So what were we saying? Where were we? We were in this Kerr index of the fiber. Okay, so this is 3.2 times 10 to the power minus 20, and the effective cross-section area is 50 micrometer. The distance it can travel such that the phase accumulated due to self-phase modulation is within pi by 10 radians. So what is the distance that it is traveling, the laser beam which you have? What is the distance that it's traveling? Can you answer this? Can you tell me which formula should I apply for this? So course effect we say is a nonlinear what? It is a nonlinear phenomena, right? So what happens is that the refractive index of the medium is proportional to E squared, and it is given by this particular formula. Here your S, what is S over here? It is your Kerr coefficient, it is your Kerr coefficient. Or the whole thing we can write as the refractive index as a function of an intensity. That will be given by your original refractive index plus N2 times I. Now here N2 is your, what is your N2 over here? It is your Kerr index. Okay. Now, so what is the formula for the change in the phase? Okay. Now this is called self-phase modulation. Okay, so the change in the phase, this is dependent on the intensity of the light. So that is your delta is equal to 2 pi by lambda times N2 times P by A, where P is the power of your laser beam, whatever is used. A is the effective area of cross section times L. L is your length of what? Length of your cell, or wherever this is happening, the fiber. L is your length of the fiber, length of the distance which is traveled by your laser beam. Okay, so now here this N2 is 1. P by A can also be written as I. Okay, P by A can also be written as I. Yeah, this will be N2 by I. I'm writing P by A as I. N2 times P by A times L. Okay, so this N2, okay. So this is the formula for your phase. So your intensity is powered by whatever is the effective cross-section area. So this would be your intensity. So what will be the change in delta N? What will be the change in the refractive index? The change in the refractive index will be given by N2I, which is given by 3.2 times 10 to the power minus 20 times this. Okay, so this will be the change in the refractive index. Why this is delta N? Because my refractive index, which is a function of intensity, is N0 minus into I. So this is your delta n. Okay, so this is your delta n. So this is your delta n. Now, so del phi would be 2 pi by lambda times delta n times L. So I know my delta phi. Delta phi has been given as pi by 10. This is my delta phi. So you can just you can just substitute it over here, and you can find what would be the length that is being traveled by my laser beam. All good?
Do we
Now,
need to convert a radian into degree?
in this case, I don't think so, because pi and pi will get simply cancelled.
Okay.
Right?
Ma'am,
Huh?
ma'am, what is the symbol of Kerr index?
What is the symbol of Kerr index?
Yes, ma'am.
I didn't get it.
N2.
N2. N2.
N2. Okay, ma'am.
N2 is Kerr index. Here I have written, no? Right?
Okay, ma'am.
S is Kerr coefficient. You forget about it right now. Just focus on this N2 when I'm writing as light as a function of the intensity. Sorry, refractive index of the medium as a function of the intensity. So that would be refractive index is a function of intensity, that is equal to N0, which is the original refractive index, plus N2 times I. Okay, and this N2 will be the symbol of the Kerr index. Okay, now let us move on to the next question. So we will now study the dispersion relation, that is refractive index ka dispersion, how it is moving on. So dispersion is what is dispersion over here? Dependence of the wavelength in the
The
group
slide
index.
is not changed. No, now it's changed. Yes.
It's changing, right? Anyone's facing the same troubles and problems? Okay,
Please change.
so it's changed. So it is dependence of the wavelength in group index. Group index over here is the refractive index, I'm telling you. So if the group velocity of any pulse is defined as the differential change in the angular frequency with respect to the differential change in the wave vector. What it meant, let me tell you. They have said group velocity. So we will say Vg is equal to group velocity is defined as differential change in angular frequency. Angular frequency is given by omega. So group velocity will be differential change in angular frequency with the change in the wave vector, and your wave vector is given by k. So this term which you call is known as the group velocity. So later on, when you'll move on with some electromagnetism course, I think you must have studied or any acoustic course where you study about waves. So there you will get to know that each if you don't have just a single of wave, but you have a train of waves, you have wave packet where there are many waves, okay, of nearby frequencies, then this wave packet travels with two velocities. One is the group velocity and the other is the phase velocity. This is called the phase velocity. I'm just telling this for your knowledge. Now what is the difference between this group velocity or phase velocity? A very, very simple example is, like, imagine that there is a marathon. Okay, there is a marathon and many people are running. So the velocity of the individual person is corresponding to the phase velocity, and the average velocity of that whole chunks, small chunks. If you see a marathon, you'll see at one place there's concentration of some people, at the other place there's concentration of other people. So those small chunks, the average velocity of so here is a marathon track, let's say. So someone is here, someone is here, someone is here, someone is here, someone is running here, someone is here. So the average velocity of this whole group is termed as the group velocity. Okay, I hope you understood. You can read about it if you are much more interested, and you will get to learn about it if you take any acoustic course, or you take electromagnetic course where you learn about waves and all. So there you'll understand the difference between the group velocity and the phase velocity. It's usually in a wave packet where you have a number of waves with almost near equal frequencies, nearly, not exactly equal. So there, that wave packet travels with a group velocity as well as a phase velocity. There are two velocities associated with it. So here what we are more concerned is with the group velocity. So group velocity of any pulse is the differential change in the angular frequency with respect to the differential change in the wave vector. So the expression of the group index, that is this Ng, this is what you call as the group index, showing dispersion would be. So let's see, how do we find this? A simple answer to this lies over here, that the wave vector, we have studied in our electromagnetic courses that the wave vector of any medium, a wave vector of a wave traveling in a medium is given by omega by c n. N is the refractive index, and this is a function of frequency. And here the wave vector is also a function of frequency. So this is the wave vector expression. And we already get to know what will be the group velocity expression. It will be simply Vg is equal to d omega dk. Now if you do the math, just do d omega dk. So here what do we get? Dk is equal to d omega by c times what? N of omega plus n of, just a second please, d of n by d omega times omega by c. Okay, so this is dk is equal to this whole thing. Now we just need to, rearrange this whole thing, right? I hope you understood this. C by, if I say, I hope you can do the maths, right? We need just d omega dk. So the whole thing comes here. C by n omega. Yeah, n omega comes here. Plus omega dn d omega. Yeah. That is equivalent to d omega dk. I hope you understood this. The maths is clear. Do let me know if there's any discrepancy or if I have done some wrong step. So this will be your group velocity. So now my omega is also equivalent to 2 pi c by lambda 0. Okay. So my d omega d lambda 0, in terms of lambda 0 I'm saying. Okay, omega is equal to 2 pi c by lambda 0. D omega by d lambda 0 is 2 pi c by minus lambda 0 squared. Okay. Now this, your dn d omega will be, what will be your dn d omega? Dn d omega will be given by this. We just take the like, you just break it. Just introduce, like over here, d lambda 0 by d lambda 0. Just introduce that and just rewrite it, rearrange it. Dn d lambda 0 times d lambda 0 d omega. And we can get d lambda 0 d omega from this expression. From this expression, what will be d omega is equal to, d omega is equal to 2 pi c by lambda 0 square minus, right, times d lambda 0. Yeah, so you get this. So you just substitute over here, plug in this equation over here. So you get minus lambda 0 square by 2 pi c times dn d omega lambda 0. So now you just put this dn and d omega in this expression, the expression over here. So you'll get the group velocity d omega dk will be over here, will be given by this. So your group index, now ng will be given by, ng will be given by c by vg, that is the group velocity of the whole thing. So we know that n is equal to c by v. We need to know the group index, the group of this thing. So ng will be equivalent to c by vg. Okay, so that is equal to n of lambda 0. What is my vg? Vg is this, c by lambda 0 minus lambda 0 dn by d lambda 0. Okay, this will be simply equivalent to n lambda 0 because c and c will get cancelled and this denominator will go to the numerator. So n lambda 0 minus lambda 0 dn d lambda 0. Okay, I hope you followed this question. Did you guys follow this?
Yes, ma'am.
It's about the dispersion relation. Okay, this is what you call the dispersion relation. So that's it for today's class. Thanks for all your attention. Thank you, class. Thanks a lot.
I have
We'll
a
be
question.
meeting. Yeah, tell me.